Bridges are monuments of human engineering, designed to conquer obstacles. Every bridge must carry its own weight, the dead load, and the live load of traffic. These forces are transferred through the structure's span, from the deck to the supports, and finally into the ground. Engineers use different designs, like beam, arch, and suspension, to manage these forces efficiently. The key is an immense safety factor. Structures are built many times stronger than they need to be, ensuring they can withstand extreme conditions and the test of time. Wind is the next load a bridge must face, invisible, constant, and sometimes cunning. There are static pushes like steady crosswinds and dynamic ones that arrive in pulses and gusts. As air flows past a deck, vortices shed in a rhythm. If that rhythm matches the bridge's own frequency, motion grows. Flutter is worse. The wind feeds the motion itself, a feedback loop that can escalate without warning. Engineers shape decks with rounded noses, tapered tails, and fairings, use trusses or open grating to let air pass, and prove it all in wind tunnels. They add dampers, cross ties, and tuned masses to bleed energy away. Control the vibration before people, traffic, and rhythm add their own. On a quiet footbridge, you might feel a gentle sway, subtle, but real, the structure breathing with each step. If footsteps or rhythmic traffic match the bridge's natural frequency, small pushes add up. Step after step, the motion can grow, just like pushing a swing at the right moment. Engineers prevent this by separating frequencies, making the bridge stiffer or heavier in the right places, so everyday rhythms don't line up. When conditions do align, the sway can build quickly, noticeable to the feet and to the eye. That's why many bridges use damping, viscous dampers and tuned mass dampers under the deck, to soak up energy and calm the motion. Today, sensors quietly watch how bridges move. When needed, engineers retrofit, add dampers, tighten connections, or guide pacing on busy footbridges. The result is simple and human, stable paths and smooth roads. So the structure carries our rhythm without being carried away by it. Bridges span rivers and valleys by channeling forces into shapes that can hold them. Beam, arch, and suspension designs guide weight along trusses, cables, and pylons into the ground. Two loads matter most: dead load, the bridge itself, and live load, traffic, wind, and weather that change with time. From deck to girders or arch, through bearings into piers and down to foundations, the load path keeps stresses controlled. Engineers add redundancy, safety factors, and regular inspection so a single failure doesn't become a collapse. Safety begins long before traffic rolls across a span. Inspectors walk the catwalks and underdeck paths on a fixed cycle, recording each check. Bolts, bearings, and expansion joints are examined up close. Gloved hands place small sensors on steel and concrete to listen for stress. Non-destructive tests read what eyes can't. Ultrasound looks inside metal, ground-penetrating radar maps hidden voids, and thermal scans reveal moisture. Strain gauges and fiber optic lines track tiny movements as the bridge flexes, streaming data to an always-on watch. That stream of information guides maintenance before problems grow. Crews schedule tightening, resurfacing, and part replacements at the right time. With each cycle, we learn and design the next bridges to be safer, smarter, and to last longer.